A few out there still over tea, but I think perhaps we should start up. So the final session today, we've got 3 half-hour slots, 3 half-hour talks, and then there's something called The Future, which, as I mentioned yesterday, is really a chance just to have an open discussion about follow-up to this program, and that probably won't take half an hour, but an opportunity for discussion there. So, to start off, very pleased to introduce Grigorios Loukides, who's now at King's College, was at Cardiff, and over to you, Grigorios.
Thank you for the introduction. Thank you all for attending. My talk has a very general title, but it's quite specific, as you will realize. So the title is Anonymization of High-Dimensional Datasets from Electronic Health Record Data. So I had to place it in the area that I'm working on, which is data mining. And you already know that big data is also about variety. So we have, can you hear me back? Yeah. At the back, can you hear me? Yeah. Okay, good, because I think that's not working. So big data is all about variety, and we have to deal with complex data. One way to see this is the famous H theorem in a popular data mining paper by Xin-Dong Wu, which emphasizes that big data is useful for exploring complex and evolving relationships. One difficulty to explore such relationships is, of course, high dimensionality. And the data shield talk just before kind of introduced that sort of problem, right? When we have high dimensional data, it's more difficult to analyze, and as we'll see, it's more difficult to protect. So this talk is about high dimensional data protection. And I said that the talk is specific because we deal with a certain type of high dimensional datasets, which we term RT datasets, and actually we can think of them as datasets which have some relational attributes and a set valued attribute. Here, for example, I have an RT dataset which contains demographics about people and also a set of diagnosis codes. So each number is a different diagnosis that a patient has been diagnosed with. That sort of data, the RT datasets, are useful in practice for various medical analyses. And examples include patient risk prediction in the context of insurance programs like Medicare Advantage in the US, several types of studies like cancer research studies, and also exploration and visualization in safe havens, data shield, and similar secure systems. So the general idea is that for certain analysis, we require to analyze demographics and diagnosis codes together. The talk is specific because it uses material of 2 works that we have been doing. And this is work led by a PhD student at the University of Peloponnese in Greece, and it's also done in collaboration with IBM Watson. So we published it in one paper, ECML PKD 2013, and we have a paper coming out in Journal of Biomedical Informatics. This is where we talk about the specific problem of anonymizing demographics and diagnosis codes together. So our goal is twofold. First, we try to prevent re-identification or identity disclosure. So this is our privacy goal. The fact that our data has demographics and diagnosis codes makes protection more challenging than simply protecting demographics and or protecting diagnosis codes. And here is a simple example why. Assume that an attacker knows that Zoe here is 30 years old and has one diagnosis, 493.2. If we apply one model to demographics and another model to diagnosis codes separately, then if the attacker knows both types of information, he can still perform identity disclosure. So here, the data is 2 anonymous with respect to demographics and 2 anonymous with respect to diagnosis codes, but then this link is unique. So the probability of identity disclosure under our assumptions is 1, is the maximum. So we try to prevent this attack. And at the same time, we try to preserve data utility. And data utility boils down into two things. The first thing is to support case count studies with no loss of accuracy. So here we are in a setting where there are certain count queries, if you like, whose accuracy we want to preserve in the anonymized data. Simply put, I want to be able to count how many people are between 28 and 30 years old, live in Europe, and have some combination of diagnosis. So this is important, for example, for verifying medical studies. At the same time, it's difficult to predict every data analysis need that we have. So we want to anonymize data in a way that remains useful for general analysis. And we will see how we try to achieve these two utility goals. So our contributions are three here. The first is one simple privacy model against re-identification, which we term KKM anonymity. If you are familiar with anonymity models, you already guess why we use this combination, but I'll explain. The second contribution is utility constraints. So it's a type of constraints that we apply to the data to support the case count studies that I mentioned. And the third contribution is a general algorithmic framework whose idea is to bound the information loss in demographics and incur minimal information loss in diagnosis codes, while also trying to satisfy the utility constraints. Okay, so before I present the contributions of our work, I'd like to briefly mention some related work. In medical data publishing, there are three threats: identity disclosure or re-identification, membership disclosure, which actually is about identifying whether a record of some patient is included in the published dataset, and attribute or sensitive information disclosure, which is about finding and associating a patient with information that they don't want to be associated with, sensitive values, if you like. Okay, and there are fortunately a lot of privacy models for all of these threats. Our focus is on syntactic models, which basically impose some restrictions on the form of the published data. And you know, for example, for demographics or relational data in general, there is k-anonymity for identity disclosure, and there is also KM anonymity for diagnosis codes or transaction data, set value data. And there are many other models like L-diversity for attribute disclosure, etc. Also, there are semantic models which try to preserve privacy in a computation, and we have heard a lot of excellent talks about models like differential privacy, and there are others, differential identifiability and pufferfish, blowfish, etc. As I said, our focus is on syntactic models. And for the type of data that I mentioned, the RT datasets, there are two existing algorithms which were developed independently and concurrently for that one, and after our work for that one. So there are very few algorithms to deal with k-anonymizing RT datasets. The first algorithm by Takahashi and others applies k-anonymity and treats diagnosis codes as relational attributes. So you probably guessed that because the data is high dimensional, if we apply k-anonymity to such data, we have a high information loss. So it's not a very good algorithm in terms of information loss. The other algorithm by Mohammed and others applies differential privacy, so it uses semantic models, and none of these algorithms have taken into account utility constraints. So in our work, we deal with syntactic data, syntactic models, and we take into account utility constraints, which are very important in medicine. Also, we see an increasing number of systems for anonymizing data. Today, we have heard about ARX, there are others, and there is one that we developed called Secreta, which deals with this type of RT datasets. But again, it doesn't take into account utility constraints. Now let me discuss our contributions. I said that our first contribution is a privacy model called KKM anonymity. So basically here, we consider an attacker who has two types of simple knowledge. He knows any combination of demographics about a patient and a or fewer diagnosis codes. M is a parameter that can be set by the user. And we say that by knowing this and applying our model, the attacker cannot distinguish the patient's record from at least k-1 other records. So you can see here that this model is a combination of k-anonymity for relational data and km anonymity, which is a type of k-anonymity restricted to any subset of M diagnosis codes to transaction data. And the protection it offers, it is against identity disclosure only, without any background knowledge. So in the example,
what do you mean by any combination of demographics, and also M for every person, for all of them? I just don't understand.
So thank you for the question. So the example will clarify this point. The attacker knows any combination of demographics. This means, for example, the attacker can know the value of age, the origin, and gender. So, or it can know just the age and origin, or origin and gender, any subset. So it can know all the demographics, like in k-anonymity, or the attacker can be weaker and know subset. So for km anonymity, let's say M is equal to 1. The attacker can know any diagnosis codes, but just one, not more, if M is equal to 1. If M has the maximum length of the transaction, he can know all the diagnosis codes or any subset. So M is a parameter, and because the data can be very high dimensional, for example, there were patients with 100 diagnoses in real data sets, we use M as a parameter to limit the background knowledge. And the type of protection we offer is that if you have this background knowledge, there are at least k different records that you can link with. So here in my example, if the attacker knows 30 and 493.2.2, there are 3 records that have this diagnosis code and also the value 30. There are also extensions of the model for preventing attribute disclosure, but I won't discuss them. Okay, so that was our privacy model. Now let me briefly explain the concept of utility constraints. The utility constraints basically model the maximum allowable level of generalization, how general, how abstract we can make our data, so that it is still useful for the intended medical studies, the count studies that I mentioned before. So, for example, I will present this example here, which will explain the concept. We treat an ordered set of values as a utility constraint. And we can see here that there are values for each attribute. So there is one value for the demographic age, and it has a range, which says that I want my generalized data to contain values between 18 and 40, because this is needed by my study. If you give me 41, it's not good for me, because I cannot accurately count how many people have this age value. And the same with other demographics and diagnosis codes. So we take these sort of constraints into account in our anonymization process to ensure that the data is useful for the intended analysis. One difficulty is that there are many different utility constraints and there are conflicts between them. So we need to impose more restrictions in the way that we can form these constraints. So if a constraint says anything is fine for me, and the other constraint says I want the data to be basically original, any interval should be very, very small. We cannot satisfy both of them together. So in the paper we have some theory for to deal with these problems. And I said that in addition to the intended studies, we want to support the general analysis tasks. For this we need to minimize information loss, how distorted will be the data. And since we talk about generalized data, we want to generalize data with short intervals so that people know can identify the values fairly accurately. So to study our problem, we consider generalization, and we have 2 functions. Basically, we replace the value in a demographic attribute by a range, as I showed before, or by a collection of values, if the demographic attribute is numerical or categorical. And for diagnosis codes, we replace one diagnosis code with a set of codes. So this means that the patient can have any non-empty subset in the set of diagnosis codes that we deal with. Now we want to see how large is the information loss. And for this we use two general measures, RAM for demographics and TAM for diagnosis codes. One important thing to note is that RAM is monotonic to subset relationships. So this means that smaller groups of records are better for utility. On the other hand, TAM is anti-monotonic. So here we prefer larger groups of records because we want to have a larger space to create different sets. And this is important for optimizing information loss, as I will show later. One thing to note is that these measures are general and they can be made special. They have various popular measures, information loss measures, as special cases. So we use them basically to make our framework more general. And here is what we try to do. We want to apply KKM anonymity, and one ambitious goal would be to try to anonymize the information loss in both demographics and diagnosis codes together. But even with these general measures, this is not feasible. There is no optimal solution unless the dataset has a very small size from K to up to 2K minus 1. This is because the nature of the data is so different that we cannot optimize both the measures together. And unfortunately, some multi-objective optimization strategies do not help here. The general idea is that they either incur a lot of information loss or they construct a range of too many solutions, and we are interested in just one solution. So we define the problem a little bit differently. We try to bound the level of information loss with respect to the demographics and minimize the level of information loss with respect to diagnosis codes. So we don't try to optimize both. We bound this value and try to minimize that value. At the same time, we want to satisfy the specified utility constraints, and also we don't want to suppress a lot of diagnosis codes. Actually, even in this form, the problem is challenging because it is NP-hard, as most of the other anonymization problems. Even when we don't have any utility constraints, we can allow any level of generalization. But another difficulty, another challenge of that problem is that we don't know if the utility constraints are satisfiable before we actually anonymize the data. So to deal with our problem, we resort to heuristics, and we have a general algorithmic framework which can be instantiated in different ways to give heuristic algorithms. This algorithm works in 4 phases, and here is a very brief overview. First, we want to group records with respect to demographics. Remember that we need to bound the amount of information loss in demographic attributes. So we use the utility constraints as a pre-processing, and we create a group of records that contain the same values in demographics for each different utility constraint. Then we form clusters which can become k-anonymous with respect to the demographics and have minimal information loss with respect to the RAM measure. And after we form the clusters, we merge the clusters to give more space to the diagnosis code anonymization, because our TAM gets better if our group is larger. And then after we do this, we form the groups and we apply KKM anonymization to each group separately. So this method is a type of local recoding, if you are familiar with the term. And the anonymization of that step is performed by a clustering algorithm that we propose. So some experiments, we have used 2 different sets of electronic health records. This data set contains about 200,000 records, and it is proprietary. It is provided by IBM. And that one is a smaller data set which is publicly available. It was used in an Informs data mining competition. To test utility, we have performed measures with respect to count query answering accuracy, and we show that our algorithm outperforms both existing algorithms that KKM anonymize RT datasets. So it is better in terms of supporting count queries. And in terms of utility loss, information loss, it's also better by at least 11%. Now I wanted to show how setting these utility constraints affect our ability to perform general analysis tasks on the data. And we saw that actually there is a trade-off. If we make our utility constraints stricter, So here, we want to have a very specific diagnosis codes, 3-digit diagnosis codes. While here we are okay with more general, more abstract information about diagnosis. If we have stricter constraints, then we pay a larger price in terms of information loss. So our ability to perform general analysis tasks becomes lower. And the same happens with constraints for demographics. If we allow larger ranges in, let's say, age, then our ability to analyze the data becomes better. So there is a trade-off here. In terms of efficiency, the algorithm is practical, but we are a long way from dealing with really big data. So as I said, our data set has 200,000 records. And the algorithm takes less than half an hour, and it scales subquadratically. But of course, it's far away from dealing with big data because we consider a data set that is relatively small and fits into the main memory. So to conclude, in this talk, I introduced the problem of anonymizing RT datasets, which is important for medical applications. I introduced the notion of utility constraints for such datasets, and I showed how we can deal with the problem by applying KKM anonymity. So there are a lot of avenues for future work. One avenue is in terms of privacy. We can get stronger privacy by semantic privacy models. Another important issue is about the balance between risk and utility, and also the ability to consider more clever adaptive attackers. And there was a nice talk by Brad on that. So applying game theory here. This is an interesting extension because we deal with different types of data. So the high dimensionality will change the way that this framework will be applied. And also one of our goals is to improve the efficiency and scalability of data, because actually in real applications, the data set size and high dimensionality requires more scalable methods. Thank you for your attention.
Questions? Yeah, yes, sir.
Did you consider microaggregation instead of generalization for your algorithm, or it doesn't fit the requirements?
We have not considered microaggregation, but it is possible to consider it because we form groups of records of at least k values. Then you can apply any generalization function you want, and you can, for example, apply microaggregation instead of generalization. And it would be interesting to compare the two in terms of utility as an extension.
I mean, the thing is that generalization works on the domain of the attributes, whereas microaggregation works on the actual data. So that's the difference. So it might save some utility.
Yes, that's true. And for demographics, it might save some utility. For diagnosis codes, I don't know exactly how this will play. Because if you have the set of values, what would be a good statistic to do microaggregation on the diagnosis part? So I guess it requires some more thought.
So, actually, can you play that out a little further? Because, Joseph, I think you guys have done some work in microaggregation on natural language data, right? Or was it at least, because the challenge is with categorical data, right?
Well, we have some work on categorical data. You use ontologies, and then you can do the thing as well. Centroids are the semantic categories closest to the ones you want to aggregate. That you take as the average. So you can average semantic values by using an ontology. You determine the value in the ontology that is closest to all the values to be averaged, and that's the average.
So to continue on that nice comment is that you can map our utility constraints onto your ontology as a first course level of grouping, and then try to make it better. It's like going down in the ontology, if you like. So this will require some adaptations to the specific algorithm, but the framework as a general grouping strategy, I guess, it will remain the same.
Yeah.
Thanks.
Any other questions? All right, perhaps we should move on to the next talk. So thank you once again.